Questions on the homework. What we're starting today, and really the rest of chapter 6 is solving. The rest of what we're doing is solving. We're going to be solving exponential and logarithmic equations. Now, this property that we have here, the property of equality for exponential equations, I call, and some call, the 1-to-1 property. Really what this says is if the bases are the same, if we have the same number for both bases, the only way this can work in both of the sides to be equal, or for this to be a true statement, the exponents have to be the same. If the bases on both sides are the same, and we have 1, the only way they can be equal is if the exponents are 2. That's really all this is saying. So if we look at the first example, 5 to the 3 minus 2x equals 5 to the negative x. Because both bases are 5, the only way that these can be equal is if their exponents, 3 minus 2x, is equal to negative x. If the bases are the same, and there's one of base on either side, the exponents have to be the same also. Now we need to solve for the value of x. So the first thing we can do is add 2x to both sides. So the left-hand side becomes 3. The right-hand side, negative 2x, or negative x plus 2x is x. So x is equal to 3. And if we wanted to check it, it didn't ask, but if we wanted to check it, we can plug 3 into x and see if 5 to the 3 minus 2 times 3 is equal to 5 to the negative third. 5 to the, what was it, 3 minus 2 times 3. And then we had 5 to the negative. They are the exact same value, which means that is the correct answer. So x is equal to 3. Questions on this here? Be ready for the next one. Are the bases the same? Yeah. We have 6 and 6, and we have one of them on either side. So the only way that 6 to the negative 2a is equal to 6 to the 2 minus 3a is if the exponents are the same. They're equal. So we're saying that negative 2a has to equal 2 minus 3a. What can we do first? Add 3a to both sides. Negative 3a plus 3a will cancel, giving us 2. Negative 2a plus 3a is going to be a, so a has to be 2. Questions on this one here? I know the two of y'all are taking the ACT tomorrow. Again, any equation, solve the following equation for x, solve it for y, solve it for the variable. It gives you 4 answer choices. Yes? So one of those answer choices has to work. If you're not sure, you come across one, like either one of these here, or either one of these here. I can just pick one of those values and replace a with that value. Does it make both sides have the same value? If it does, that's the correct answer. If it doesn't, throw it out, try another one. But if we were looking at this here, 3 to the 2a equals 3 to the negative a. Since the bases are the same and there's only 1 on each side, the only way this works is if the exponents are the same as, well, so we're saying 2a is equal to negative a. What can we do first? Add a to both sides. Negative a plus a is 0. Since there's nothing else on the right-hand side, it would just be 0. 2a plus a is 3a. 2 ways we can go about it from here. One, is the zero product property. Zero product property says if I have two or more things multiplied together that equal 0, one of them has to be 0. Or we can divide both sides by 3. 3a divided by 3 is just a. 0 divided by 3 is 0. This seems odd that it would be 0. We can check and make sure. 3 to the 2 times 0. That would be 3 to the 0, which is 1. 3 to the negative 0, well, that's just 3 to the 0, which is 1. The nice thing about solving exponential equations where the variable is in an exponent, the value of x does not matter. And what the result from plugging it back into the exponent does not matter as long as we have a real number. I can plug any number into an exponent. As long as it makes both sides true, we're good. I don't have any restrictions. 2 to the 2x plus 2 equals 2 to the 3x. So really what we're doing is, you don't have to rewrite it. I'm going to rewrite it. Is we're saying that because both bases are 2 and there's 1 on either side, the exponents have to be the same as well, yes? We went over this last week. If I applied log base 2 to the left-hand side, well, log base 2 of 2 is 1, or as we had it stated, log base b of b to the x is equal to x, that exponent. So if I apply log base 2 to the left-hand side, log base 2 of 2 to the 2x plus 2 is going to be 2x plus 2, yes? But I can't just do it to one side, we have to do it to both, yes? The right-hand side, log base 2 of 2 to the 3x would be 3x, because the log base 2 of 2 simplifies, yes? That's what we've been doing on all of these. The one before it, we were applying log base 3 to both sides to get the 3's to simplify. Now we just need to solve. What can we do first? Minus 2x. Since the constant terms are already on one side, might as well get the x's on the other, and it tells us it's 2. These are kind of nice. Can we make these harder? I mean, yes, we can start putting quadratics and higher degree polynomials in there. But it's really not making what we're doing here any harder. We're just adding steps. All right. Number 9, 6 to the 3m times 6 to the negative m is equal to 6 to the negative 2m. The right-hand side is fine. We have one base. But the left-hand side is not. We have 2. However, we can turn it into one base because when we multiply like bases, we add the exponents. We need it to be a single number. We need it simplified down. So if we were to write or apply log base 6 to both sides, we're applying it to one term, not 2. But just like we said before, we can set these equal to each other. But before we do that, it might be nice to simplify that exponent. 3m plus negative m is 2m. So we're saying 6 to the 2m is equal to 6 to the negative 2m. Since the bases are the same, the exponents are going to have to be the same as well. Add 2m to both sides, those would. 2m plus 2m is 4m. Divide both sides by 4. M has to be 0. Questions on this here? What values of x? What value of x makes the y values be the same? That's our solution. All right. 4 to the negative 2x times 4 to the x equals 64. Two things that we need to fix if we're going to solve this by the one-to-one property. One, we need to convert this to a single number. Since we're multiplying like bases, we can add the exponents. But also, if it's possible, I need to rewrite 64 as 4 to a power so we get the bases to be the same. Well, 4 to what power do we think is 64? That is indeed 3. So we can rewrite 64 as 4 to the third. And we can rewrite this product as 4 to the negative 2x plus x. Well, negative 2x plus x is negative x. So we're saying 4 to the negative x is equal to 4 to the third. Since the bases are the same, the exponents have to be the same as well. So we're really saying that negative x is equal to 3. At this point here, we can multiply by negative 1. We can divide by negative 1. But it tells us x is negative 3. Questions on this here? Questions on anything so far? We ready for the next one? 10 to the x is equal to 1/10 to the x minus 3. So this would be very nice if we can get both of the bases to be the same, especially for 1/10. If I could rewrite this, don't need that extra set of parentheses, and say 10 instead of 1/10, that would make things nicer, yes? But we can't. Because we can move numbers or terms from the bottom of the fraction to the top, or top of the fraction to the bottom. But by doing so, we change its exponent from positive to negative, or negative to positive. So even though it wasn't written in the denominator, we do have 10 to the first, which means when we move it to the numerator, it's now 10 to the negative first power, yes? So that makes things kind of nice. Now the other hope is that I can rewrite 100 as 10 to a power, and it would be 10 squared. Powers of powers, multiply. So we have 10 to the 2x is equal to 10 multiply here. Here we do have to distribute that negative 1 to both. We can't just multiply it to the x. So we have 10 to the 2x is equal to 10 to the negative x plus 3. Since the bases are the same, the exponents have to be the same as well. What can we do first? We can add the x to both sides. 2x plus x is 3x, and it is equal to 3. Then we can divide both sides by 3, telling us x is equal to 1. And yes, it's going to be good, especially when you replace a variable with a number, to put parentheses around it just in case. Well, 100 to the first power, lo and behold, is 100. 1/10 to the 1 minus 3 is also 100. Same value, so it's fine. What base would we want to use for the next one? What number do you think we want to get both of the bases to be? 9. Because 1/9, I can move the 9 to the numerator, which is going to make it 9 to the negative first power. 81 can be rewritten as what? 9. Mm-hmm. 9 squared is 81, so we get 9 squared to the x, which is 9 to the 2x. 1/9 we can rewrite as 9 to the negative first power. Powers of powers multiply, so it gives us 9 to the negative x minus 3. When the bases are the same, the exponents have to be the same as well. So 2x is equal to negative x minus 3. We would add x to both sides, telling us 3x is equal to negative 3. Divide both sides by 3, telling us x is negative 1. Questions on this here? We'll look at one more. Which one do y'all want to look at? Huh? The 7 one? Yeah, because the bases are not the same. And interestingly enough, what base do we want to write 343 as? 7. Because the left-hand side kind of gave that away. Because I want to get the bases to be the same. 7's prime. I cannot reduce it. I can't simplify it further. So I'm hoping that 343 can be written as 7 to a power. What's our guess? 3 would be right. Powers of powers would multiply. So we get to 7 to the 2x minus 3 is equal to 7 to the 3x plus 12. And the bases are the same, the exponents have to be the same as well. What can we do first? We can subtract 2x and 12, yes. Try not to flip our signs. So x is equal to negative 15. Questions on this here? And yes, I could go and graph both of these. ACT does have a built-in graphing calculator. It's just mainly going to graph. But I could have it graph both functions and see what value of x makes them be the same. Normally, we have an infinite number of numbers. We have the whole real number system to look at. But wait, the ACT gives me 4 choices, yes? So I can graph it and look at those 4 values of x and see which one of them makes the y values be the same. Even if it gives me a decimal approximation, I can get close. One-to-one property still. If I have one log on either side of the equal sign, and it is the same logarithm, The only way they can be equal is what's inside each logarithm is the same. Note, what's inside the logs, 1, base of a logarithm cannot be 1. 2, whatever the remainder or whatever the value of x and y is, it cannot be 0 or negative. I cannot take log of 0, does not work. I cannot take log of a negative number. If the value of x, in this case x, makes that expression be 0 or negative, we throw it out. It does not work. Even if both sides are the same, if it told me that the natural log of -1 is equal to the natural log of -1, doesn't matter. I cannot take the natural log or log of a negative number. Now, when we look at this here, we have one log on either side and they are the same, yes? So it means what's inside has to be equal. So it's telling us that 4x minus 7 has to equal x plus 5. Questions on this here? Well, yes, there is a good reason for it. What's e to the ln? Well, e to the ln, the bases that we're putting the natural log to and the base of the natural log are the same, so they would cancel out, leaving us with what's inside. That's all we're doing. Does that make sense? 4x minus 7 equals x plus 5. We can, what? Add 7 and, add 7 and subtract x. And at this point here, you see what the answer is, especially on the ACT. Go on and pick it and move on. If not, we'll do our next step, which is to divide by 3, telling us x is equal to 4. And we can plug it back in. 4 times 4 minus 7 would be 9. 4 times 4 is 16. 16 minus 7 is 9. Natural log of 9 is fine. Right-hand side, the natural log of 4 plus 5 is going to give us the natural log of 9. They're both the same. We're good. Questions on this here? Natural log of 7x minus 4 is equal to the natural log of 2x plus 11. Again, since the logs are the same and there's only one on either side, what's inside the logs must be equal. So 7x minus 4 has to equal 2x plus 11. Then we would add 4 to both sides, and then yes, we're going to definitely subtract the 2x from both sides. Telling us that 5x is equal to 15. And then last but not least, we would divide by 5, telling us x is equal to 3. Questions on these here? I'm good with these here so far. First or second one? Darling. First, ln of 5x plus 2 is equal to the natural log of x plus 10. Since the logs are the same, we're looking for what's going to make what's inside each log be the same value. Yes? X has to be 2. Questions on these here? $11 or 12? 11. Log base 12 of v squared plus 35 equals log base 12 of negative 12v minus 1. Since the logarithms are both log base 12, and I only have one of them on either side, it tells me what's inside has to be equal. And I think yours says x, yes? I'm going to switch over to x because that's what y'all's paper has. Really doesn't make a big difference. For whatever reason, I wrote x instead of v. Since we have a quadratic term, we need to get this equation equal to 0, yes? What can we do first? We can add 12x. We could have also added 1 first. It really doesn't matter. And that gets us, once we move everything over, we get x squared plus 12x plus 36 is equal to 0. Now we need to solve this here. We can factor, we can graph, we can use completing the square, we can use quadratic formula. Nice thing about the ACT, again, I'm going to say it so many times today and I'm going to keep saying it. One of those 4 answers has to be true, yes? Graphing's nice if the solutions are integers, yes? Do we know that the solutions are integers? We can hope. But especially on the ACT, it gives me 4 numbers that do not have decimals or radicals. That means the answers have to be integers, yes? Which means we can factor it, which also means we can graph it. So the test tells me integer solutions. The only real time that won't work is if it tells you solve the following equation for x, or find the approximate value, find the, once they tell you we're rounding, it's not going to be integers. Even if they do show us integer solutions, they have been approximated, they've been rounded. But they give me integer numbers here, we can graph it. Also means we can factor it. Third term's positive, so the signs are the same and match the sign of the middle term, yes? Which would be positive and positive. Factors of x squared are. What can we say about our solutions? Are they going to be positive or negative? Negative, because the only way I can plug a value in here and add it to a number and get 0 is if this value of x is negative, yes? Positive answer is gone. Factors of 36. 1 and 36. 2 and 18. 3 and 12. 4 and 9. 5 doesn't work, but 6 and 6. What do we think? 6 and 6? Yes, I agree. That would give us a middle term of 12. So we're saying that x plus 6 is equal to 0 and x plus 6 is 0. Subtract 6, we get x is equal to negative 6. We have 2 solutions. They're not unique solutions, but we do have 2 solutions. Questions on this here? Now again, I said that we cannot have a negative or 0 in a log, but we're saying that x is negative 6, yes? All right, I'm going to erase all this. Let's look at the left side, because we have log base 12 of negative 6 squared plus 35. Negative 6 squared, negative 6 times negative 6 is positive 36. And 36 plus 35 is 71. Is what's inside the logarithm now negative or still negative? No, I don't care. It does not care that I plugged a negative in. It says, is this final number negative? If it is, can't take it. If it's 0, can't have it. But positive 71, I can take log base 12 of 71. That is fine. We can check the other side. Negative 6 times negative 12, negative and negative make positive. 6 times 12 is 72. 72 minus 1, 71. So these are indeed equal. This works. What I'm curious about, I think this might work. I'm going to plug in. No, it's not going to give us the right number. Positive 6. Because this here, I'm going to fix that just to show this point. This would be 36 plus 35. 36 plus 35 is 71. This here would give us negative 72 plus 1. I can't have log of a negative. Even if it told me log base 12 of negative 71 is equal to log base 12 of negative 71, doesn't matter. I cannot take log of a negative number. Neither one of these exists. Doesn't matter that I have the same thing on both sides. I cannot do either operation. Does that make sense? Questions on any of this? That's it. And I'd say the biggest thing with the ACT was solving equations. If you're not sure, plug values in.